This webinar is sponsored by NEC Corporation, a $37 billion technology leader with a 100-year history of innovation. NEC's Programmable Flow Networking Suite was the first data center-grade SDN leveraging the OpenFlow protocol. Deployed globally today, Programmable Flow transforms network performance and agility by providing production-ready SDN solutions that increase flexibility, visibility, and efficiency while reducing complexity and costs.
To find additional SDN, OpenFlow, and network function virtualization resources, visit ipspace.net/SDN. Every time I talk about software-defined networking, I first struggle with the definition. What exactly is software-defined networking? There's one definition we have. Is a definition of the organization that first mentioned this acronym, the Open Networking Foundation. And what they're saying is, well, software-defined networking is the physical separation of the control plane from the forwarding plane. So what they're saying is you must have two devices, two physical devices, one of them being the controller and the other one being the switch. And a control plane has to be able to control several devices. So if you have just a controller sitting on top of the switch, this doesn't count under their definition. As soon as they came out with SDN and SDN and OpenFlow became a huge hype, obviously vendors jumped in and started claiming that SDN is anything. Anything that can be programmed is SDN. I'm joking that most vendors approach SDN from the perspective of, well, let's see what we can ship today and let's call that SDN and let's try to persuade everyone else that SDN is what we call SDN, also known as SDN washing. And then there are the startups that say, well, if we want VC funding, maybe we should start talking about doing something that sounds like SDN, and if we use the right magic buzzwords, we will get funding. I know that this has been happening in the past. But let's forget the marketing and financial implications of the SDN word, and let's ask ourselves, is the ONF definition too restrictive? Shall we limit our understanding of SDN to their definition? And the first problem I have with the term itself is that since the days of thick coax cables and unmanaged hubs, all other networking devices had software. The device behavior was always defined by the software that was running on the device. So why are we talking about software-defined networking? For me, it's a bad term, honestly, because networking was always defined by the software running in the control plane. But let's forget that. Let's ask ourselves, is this software-defined thing really something new? Or is it just hype and marketing gone really bad? Let's see what were the motivations behind the movement that was later called SDN. If you watch the videos from the very first OpenFlow symposium that we had 2.5 years ago in September of 2011, there were Google, Yahoo, and a number of other companies giving their OpenFlow presentations. The Google and Yahoo presentations were very clear. They wanted to build their own software. In Google's case, they actually did it. They just wanted to have white label switches on which they could put their own software, and ideally their software would be running somewhere on a server farm so that they could scale that out. Yahoo wanted to have their own features, and no vendor was willing to implement them. So they said, we need something where we can control how our devices work, because we don't think that the vendors are implementing the features that we think we need in our network. In both cases, these were huge organizations with very specific requirements that wanted to do something very special that made perfect sense for them. And it absolutely does. But they are very specific because they have the resources to develop the software to run on their switches. Question I got from Adolfo: what type of features Yahoo wanted and no vendors provided? If I remember correctly, they were talking about the fact that they know where everything is connected in their network, and yet they have to run spanning tree and routing protocols and so on, even though they know exactly where something is and they could provision everything from the orchestration system. Finally, Facebook has the Open Compute initiative, and they already printed the blueprint for a top-of-rack switch, and now they need some software to run on the switch. Yet again, it would be ideal if that software would work with something like OpenFlow, because then they could buy any OpenFlow switch on the market, put their software as the controller to work with a switch or a set of switches, and they could have multiple sources of their switches with the same software running on them. As I said, this makes perfect sense to those three companies. In my world of smaller service providers, enterprise customers, small public clouds, private clouds, and so on, what we really need is faster provisioning. The other thing we desperately need is the ability to centralize the intelligence, centralize the policy, do something with that, and push it out. And for that, for the push it out phase, we need programmable network elements. And you know how bad some of the current equipment is. You have something like netconf, but what you can do is you can push CLI commands through netconf, so you have nothing. I would argue that the second set of requirements actually makes more sense for most customers apart from the very big cloud providers. Next, if we focus on the second set of requirements, we had SDN in 1992. This is the system we built in 1992, and we used it to provision our network because we were an internet service provider in those days. We had some central database. It was probably a text file. We had some web UI, and then we had a Perl script that would generate the configs for our core router, which was an AGS Plus, and our access servers, which were simple 16-port access servers. We downloaded the configurations, and it all worked. I haven't seen many people doing that afterwards. So yes, there are a few customers that are still doing that. I know of a few service providers that actually provision services these days using something like this, but everyone was doing it in 1990s. So why have we stopped? What went wrong? I'm claiming that we stopped doing that because networks became mission critical and no one wanted to play with the network. So the moment networks became really mission critical, we were told to stop doing this. There were a number of reasons we were told to stop doing this. Networking people aren't exactly known for their programming skills. So there was definitely the lack of programming skills. There was the lack of programmatic interfaces in the devices. What we were doing here was totally unreliable. We used probably R shell or R copy, and later people were using SSH or Telnet and expect scripts. These things are simply too unreliable to use in a production network. You can trust me on that because we also had to write a system to control remote labs, and we had to interact with a number of different boxes from different vendors. Making those things work through a telnet session is a nightmare. Covering all sorts of potential error messages that come back, that just doesn't work. So the lack of some programmatic interface was another crucial factor. Next one, You cannot configure a Cisco box, a Juniper box, an HP box, and an Arista box in the same way. Even when they have programmatic interfaces, they are all different. That's another thing that stopped people from doing these things, because everyone went like, well, I might invest a lot of my time in writing this, but what happens when we have to change the vendor? IETF didn't do anything to help us improve things. They had netconf, and then they decided that they need a modeling language. So instead of giving us something like SNMP MIBs, they spent years on defining the language. And even today, there isn't an RFC out there that would tell you how to configure something as simple as an IP address on an interface with netconf in a standard way. And you know that it will be years before vendors implement whatever RFC will eventually come out. In summary, they didn't trust us. We were told to stop doing this because they didn't trust us. Isn't the lack of broad programming skills the same within the customer's base today as it was in the past? Absolutely right. And that's why there are a number of people out there telling everyone to start learning how to program. On the other hand, programming the network devices a few years ago was really an awful job. Let's say you want to program a switch from some vendor and it supports netconf. It's pretty hard to get an environment up and running on your workstation that has all the modules you need to run netconf in your favorite programming or scripting language. Now that the device vendors have finally figured out that there is something called HTTP and something called REST API, and they all offer that, all of a sudden we can program any device through almost any scripting environment. So the barrier to entry is significantly lower than it has been in the past. Next one, how do you define Cisco ACI or VMware NSX solution from the SDN definition perspective? VMware NSX fits the stricter definition of SDN because they actually have an OpenFlow controller that is installing forwarding entries into the hypervisor switches. They both also fit the, let's say, broader definition of something which is programmable and uses some central intelligence. I cannot comment on Cisco ACI anymore because I have to see it first. Next one from Kulin, more of a comment. If you have different vendors, you could in theory use something like tail-F network control system to abstract the different semantics and give the customer a common platform. I absolutely agree with you, and that's why I would personally call tail-F an SDN controller, even though it doesn't fit the definition of offloaded control plane. Next one, do we still lack the programming skills? I would say yes. I've seen a lot of networking engineers who said, I went in networking just so I don't have to program things. So yes, I think that particularly in networking, there is a lack of programming skills. Next one is SDN not more about managing flows instead of managing device configs? You see, that depends on the definition. If you stay with the strict definition as promoted by ONF, then you're absolutely right. Then you need something like an OpenFlow controller that will manage flows. If you're happy with having programmable network elements, then it doesn't matter what level you're working on as long as you get your job done, and I'll come back to that in a few slides. Here I have a perfect one from Martin saying, can't a chassis platform be considered as a basic form of SDN because the CPU card is separated from the line card, so forwarding is physically separated from the control plane? I totally agree with you. And that's the argument I'm always making, that we had this before. This is nothing new. If you take a look at the architectures like Juniper's EX8200 with the external XRE200, if I remember correctly, that fits the ONF definition of SDN perfectly, as does, for example, Cisco's Nexus 1000V and a number of other things that were in production years before ONF came out with SDN. But let's not go there. Very valid comment from Terry Slattery. There is one problem of different configuration interfaces on different switches or routers or what have you. And the bigger problem is the differences in semantics between different vendors and even models within a single vendor, like QoS on different switches. I totally agree with you, and I don't think we are anywhere near a solution there. Now you know that we have like two conflicting definitions of SDN. The other one is strict. You need a controller, it has to have the control plane, and the switches should be dumb and have just the forwarding plane. And the other one is way broader, and it's saying, well, you know, maybe we should consider anything that is programmable to be something SDN-ish. Let's forget about the definitions and let's ask ourselves, what would be the perfect use cases? There are things that we do well. Destination-only, hop-by-hop, layer 3 forwarding is a solved problem. Anyone who is trying to solve this with new technologies, architectures, what have you, is probably focusing on the wrong problem. Then there are things we don't do so well, which is large-scale provisioning or orchestration, synchronized policies, be it security, QoS, or whatever else. One I particularly like is traffic engineering. Any service provider who ever had to implement MPLS traffic engineering in a large network knows that it's a royal pain. Because by definition, something like MPLS traffic engineering trying to fit bandwidth requirements across a constrained network is what the theoreticians would call a knapsack problem. You're trying to fit as many items into a knapsack as possible. That problem is really hard from the theoretical perspective. Trying to solve this in a distributed system is mission impossible. There are a number of systems out there that solve the traffic engineering issue in a centralized manner through a centralized controller. Unfortunately, not many people are using them. For example, I know that people have been doing centralized traffic matrix computation 15 years ago. There was a company that had a great product, Carridon, if I remember correctly, and yet again, not many people were doing that. If you want to do it today, there is path computation element, RFC, unfortunately not implemented by many vendors. So yet again, you could do that. And then there are things that we don't do at all, like QoS-based forwarding, or forwarding adaptations based on current load, or forwarding based on source and destination, or insertion of features in the forwarding path. All these things can be done with our today's forwarding hardware, but they are very hard to do in an asynchronous distributed system with eventual consistency. That's, for example, why Cisco stopped supporting load as one of the parameters of EIGRP. Because if you try to take care of load in a distributed asynchronous system, you will just get traffic oscillations. Let's revisit the principles of SDN as I understand them. We should have centralized visibility, be it centralized controllers or however you want to call them. Then you should be able to make the decisions based on centralized end-to-end visibility. For example, traffic engineering is a great example there, or end-to-end QoS policy, or applying security to all the edges of the network consistently. And then when those decisions are made, there has to be some automatic way to configure the network devices. That automatic way can be either flow installation in the strict definition of SDN or anything else that gets the job done in a more relaxed definition. Of course, every time I mention these three principles, I get the usual objections. But wasn't this promised years ago with network management systems? If we have central controller, what happens when the network partitions? This didn't work in the past. Why should it work now? I have no good answers. All these are very valid objections. The same people that were writing network management systems are probably writing a controller or two today. The only chance we have of getting things done differently this time is if we take it in our own hands and start programming things that really matter to us. Can we do it? It turns out that we can. There are loads of existing mechanisms that we can use today. There's netconf. Yes, the schema is not standardized. Configuring Cisco box is different than configuring Juniper box. But if you want to have something that can consistently change device configuration and report an error if an error happens, you can use netconf. If you want to influence the forwarding behavior, BGP is the perfect protocol to use, and later on I'll show you how Microsoft is using that. By the way, a large number of internet service providers are using a nice trick called remote triggered black holing, where you can kill the traffic based on its source address by sending a BGP update for that address pointing to the null interface. That's SDN. They have a system that figures out that a denial of service attack is underway. They figure out which sources and destinations are problematic. They send that information out to all the boxes in their network. If that isn't SDN, I don't know what is. Then there is the PCEP, which I already mentioned, which allows you to install traffic engineering paths from the central controller. Then there are things which you can use to directly influence the forwarding table today. There is BGP flow spec. It's functionally almost equivalent to OpenFlow. It allows you to install 5 tuples to block or reroute traffic to certain destinations or traffic matching a particular protocol or port number. CDN providers, I think it's Cloudflare in particular, are using that to do denial of service prevention. So they can use the BGP flow specs to drop the offending traffic that they identify at the edge of the network based on source and destination address and the port numbers. Things that you can do with OpenFlow, as we'll see later on, you could do with BGP flow spec, and that's an old RFC. And then every vendor has some API today, and almost every vendor has some scripting capabilities. However, there are things we can do, and there are things we cannot do. Configuring a device, changing device configuration, anything else that happens on the management plane, that's easy to do. You just use netconf. You want to modify the forwarding table, you can do this with BGP, or you can use BGP flow spec if you have the boxes that support it. Simple edge policy enforcement. As soon as you can get the box to communicate with some radius server, the radius server can download the access control list on the edge. So these are things we can do. Topology discovery is harder to do. Extraction is even harder. There are mechanisms that are being discussed in IETF where you could extract OSPF or ISIS topology in BGP updates for easier consumption. Worst case, you just connect your controller as an OSPF router in your network, and all the OSPF neighbors will dump the topology database into your box, and you can see what the network looks like. Non-standard forwarding models like source-based IP routing They are harder to do because there is no good interface to do it. Every switch, every router has some sort of policy-based routing, but there is no programmatic interface that we can use to do that. Multi-vendor solutions are a major pain. If you want your solution to work in a multi-vendor environment, you usually have to write your own abstraction layer today and then adaptation modules below that to interact with different devices. End-to-end consistency, end-to-end visibility, transactional consistency, really hard to do. I've only seen one company that does it successfully. This is TailF I already mentioned. Maybe there are other people out there that can do it with the existing devices, but this is really a tough problem. Implementing new control plane protocols, mission impossible. We cannot do it with today's tools. Today meaning pre-OpenFlow. Modification of existing control plane protocol behavior, like I want BGP to work differently, mission impossible. You cannot really change the way the software on the box works. You can interact with it. You can try to persuade it to work differently within the scope of how it works, but getting brand new functionality really hard. Anyhow, even what we have today is usually good enough. So what Microsoft did is they first built their data center using exclusively BGP. If anyone wants to know the reasoning behind that, it's well documented in an informational RFC published by Peter Lapucho. So just search for Lapucho on IETF.org and you'll find that RFC, in which he explains the reasoning for BGP-only data center as well as how they did it. I think there's also an article that they published plus a number of NANOC presentations. So if you're interested in that particular part, you'll find everything you need on the internet. And then once they had that, they started developing a controller that connects through BGP to all these switches and routers, and it can override any forwarding decision through iBGP updates. So they can effectively get the network topology from smart BGP updates. They can get the forwarding information from every single box. They can reconstruct that in the controller as the network topology and forwarding model. And then they can start through iBGP updates. They can start to influence the behavior and the forwarding tables of individual switches. The first application they did was graceful reconfigurations and graceful shutdowns. They can use the controller to poison the paths going through a certain switch. And when the whole network reconverges, which they can monitor because they are monitoring all the updates coming in, they can tell the operator that the switch can be turned off. The next step, they're talking about traffic steering. And once you have something like this in place, really sky is the limit. As long as you stay within the scope of destination-only forwarding, which is what BGP supports, you can do anything you wish. On the other hand, there are things that we simply cannot do with existing protocols. And this is where the new protocols are coming in. Primarily OpenFlow, and I'll only describe OpenFlow because out of these, it's the one that's richest in functionality, and it's being standardized and implemented by numerous vendors. Then there is OVSDB, which started as a configuration protocol for Open vSwitch, but now they're using it as a generic data interchange mechanism. So they're also pushing mapping entries and forwarding entries through OVSDB. I2RS is interfaced to the routing system. So it's a protocol that interfaces with the IP routing table, not the forwarding table. Then we have the OFConfig, which is the OpenFlow configuration protocol, which you need to configure OpenFlow switches. A number of vendors are using things like, for example, XMPP, which is really a chat protocol to configure the devices. For example, Arista is doing that. And Cisco is pushing 1PK as an API that will allow you to program anything. within Cisco iOS. Out of this, I think OpenFlow is the most mature. That's why I'll focus on OpenFlow in the next section of the webinar. You just need to remember where all the others fit in.
Thank you for attending this webinar sponsored by NEC Corporation. For more information on NEC or the Programmable Flow Networking Suite, visit us online at necam.com/SDN. To arrange a demo or to pilot Programmable Flow SDN, call your NEC account rep or contact NEC directly at necam.com/contact us. Thank you for your interest in NEC's Programmable Flow Networking Suite.
Additional SDN, OpenFlow, and network function virtualization webinars, recordings, and workshops, as well as other resources like books and case studies, are waiting for you at ipspace.net/SDN.